question was asked about one of the assigned questions on page 649, question number 20A. What the heck happens here is often what I get asked. In this case, chlorous acid, HClO3, is both the oxidized species and the reduced species. Because if you notice, we have two chlorine compounds on the product side. Let's begin balancing this as we would normally, and then I'm going to show you a strategy that can be really helpful to understand what's happening here. All right, let's go. All right, now we're going to identify our oxidized and reduced species. All right, so now we've got it set up where we've got our oxidation numbers listed, and we've described each half reaction. But this is an awful lot to hold in our heads, a lot of balls in the air that we're juggling right now, because HClO3 is both the reactant of our reduction half reaction and the reactant of our oxidation half reaction. So far, we've only been demonstrated the oxidation number method, but there is another method. Let's describe the reduction half of the reaction separate from this entire, the oxidation half reaction. All right, let's go. All right, so now we've described each half of the reaction. I've tried my best to color code those two processes as it relates to our oxidation number method. Let's balance each half of the reaction before we balance our electrons and then recombine the half reactions. Okay, let's start by balancing each half reaction. We're going to assume it's under acidic conditions. We need to do this in order to balance this half of the reaction. You could also balance it under basic conditions, but so long as you're consistent between the two, when we recombine them, it'll be much easier. All right, so we added a water molecule so that we would have 3 oxygens on the product side to match the 3 oxygens on the reactant side. We added the hydrogen ion to the left-hand side, so we would have 2 hydrogen atoms to match the 2 hydrogen atoms on the product side. Let's balance the oxidation half now. All right, one thing I want you guys to notice right now is that the sum of all the charges on our reactant side and our reduction half reaction is 0 net charge. We have a positive sign, we have a negative sign, they cancel out, 0 net charge. On our product side, we have 0 net charge. A great way to check your work as you're doing this is to make sure that the charge is conserved, the same charge on both sides of our reactant and product. Let's look at the next. Here we have 0 net charge on the reactant side. There are no charged particles. On the product side, we have 2 negative charges and we have 2 positive charges. There's 0 net here as well. So this is just a quick check to make sure that we have everything set up properly. Now, in order for us to balance the electrons, we need to have 2 electrons being reduced for every 2 electrons being oxidized. So our reduction half reaction needs to be doubled in order for us to balance the electrons gained and lost. Let's rewrite these equations and add them back together. So we use the distributive property here. Now let's add our reduction half reaction and our oxidation half reaction together to get our balanced chemical equation. First, let's identify a chemical species that we can reduce. If we start and finish with 2 electrons, we can cancel those. If we start and finish with 2 hydrogen ions, it didn't undergo change, we can cancel those too. If we start with 1 water and finish with 2 waters, we can cancel out one of those waters. Let's group these together now. This is our balanced equation. We did it. Good job, everybody. All right. Good luck. Keep working hard. I appreciate you guys.